So for this first talk of the second session will be Loïc Rouquette, who's going to talk about a tool for automatically generation of abstraction-based differential attack, Tagada.
Thank you for the introduction. The talk will be about how do we automatically compute differential cryptanalysis on ciphers using directed acyclic graphs. So firstly, why do we create Tagada? So at the beginning, when we see how do cryptanalysis was done, it was integrated attacks. So the authors write directly attacks on ciphers. And the information between the attacks and the ciphers are mixed together. And it was quite hard to debug the implementation if the implementation were wrong. And it was hard to replicate the same attacks on different ciphers. So a first step, it was to use automatic solvers such as SAT, ILP, or CP solvers. With this kind of representation, we can separate the modeling phase and the solving phase. So we translate the cipher into a mathematical model, and then the solver needs to resolve our problem. And after that, we have the solution of what we ask. In Tagada, we go one step further by separating the model into two parts. So in the first part, we want to represent directly what is the attack we want to do. And in the second part, we have the cipher representation. So why we do this? It's because if we have a distinct representation for the attack and the cipher, we have an abstraction of the attack and an abstraction of all the cipher in a uniform representation. We are able to reproduce the attack on all kinds of ciphers. So how block ciphers are created? So we know that block ciphers are using common operators, and they are also using common structures. We know three main families of a block cipher, which are SPN, phase-10 networks, and ARX. And the idea is that if we know the properties of the operators or some property of the structures, we are able to use the same property on a different kind of ciphers that look like the same. So, for example, we do not see well here, but we have the AES representation on the left and the Midori representation on the right. And you can see that the structure of the cipher is quite the same. So for AES, we have a key schedule, and so the key XOR just here with the plain text. After that, we use an S-box. And after that, we use a mixed shift row, sorry, that shifts each row by a given number of column. And in the last operator is the mixed column. So we compute a matrix multiplication between this state and fixed matrix. On the right part, we have quite the same thing. We have a XOR between a part of the key. It depends on the version of Midori. After that, we use an S-box also. We have a different permutation, but it's quite the same in AES and Midori. And in the last part, we have a mixed column multiplication. It's just that we use a different matrix. Okay. So we see that we have two common representation, and the cipher are quite the same. But if we have integrated attack, you need to re-implement all the attack for the both cipher. with Tagada, what we do is that once you have created the attack, you are able to reproduce the attack on the two ciphers. So the expected benefit of this is when we have extract a witness of one operator or one structure of one kind of ciphers, we are able to use the same weakness on the other ciphers that use the same constructions. So what is Tagada? So Tagada is a library that work on a diacritic acyclic graph. And we use the following workflow to compute differential and truncated differential distinguishers. So at the left, you have the cipher. The only manual phase of the library is to implement a cipher representation. So this is called a spec. So in spec, we have an algorithm that produces the JSON data that will be given to the solver. When we have this, you have the diacritic acyclic graph. With this graph, you are able to test if the implementation is correct or not. We will see it later. You can differentiate the graph in order to produce a format that will be created in order to compute differential attacks. If we want to compute other attacks like linear attacks or other things, we need to create another representation of the data. And with this phase, in Tagada, we work in two steps. So in the first step, we use truncated differential representation. And in the second step, we use a differential representation. So when you have the differential graph, you can truncate it to compute the truncated differential DAG. With the truncated differential DAG, you are able to compute directly the truncated differential characteristic, the best one. And with the truncated differential DAG and the differential DAG, you are able to compute the best differential characteristic. Okay, so the data representation of Tagada is using a diacritic acyclic graph. So we are using a bipartite graph. The bipartite graph, I think, yeah. So we are using a bipartite graph. So the nodes are the concatenation of the operators and the state of the cipher. Here we have a really simple cipher. So we have two inputs, which are M, that can be the plain text, and key, that can be the key, a constant, and this the XOR of the three variables go through an S-box, and we have the output, which is the ciphertext C. So you can see the representation of the data that is on the middle. So each state is represented by a square, and each operator is represented by a circle. We have the three states that go to the XOR. We need to create temporary variables in order to represent the intermediate states that go through the S-box. And at the output, we have the C variables. So this is a graphical representation. And if we want to have the mathematical representation in the form of a graph, we have G, which is equals to N and E, and the N is all the state and all the operators of the cipher. And the H is how do we link the state and the operations together. So, for example, we have M, K, and 10, which is XOR together, and that gives a Y value. And we have a second link, which links the Y value through the S-box to the C variable. Okay, so the first phase, as I already say, was to transform the cipher representation into a data that can be read by the solver. So this step is done manually. So, for example, how we can do this, on the right part, you have the specification of warp. So you have the computation of the key schedule on the first row. You can see that, in fact, you only split the key into two parts. This is done with with this line here. So we make a slice of 16 bytes for key, and after that we use the two subkey, key 0 and key 1. And you can see that the implementation is quite a straightforward transformation of the description of the cipher. So we just have a few helpers that allow to rename the variables in order to easily debug the solution. So we have the two keys here. After that, we iterate through the number of rounds, which is fixed in the definition of warp. But when we compute the differential distinguisher, maybe we want to stop the distinguisher before the end of the cipher, so we are able to configure it. After that, we have the round function. So you have the representation here, and you can see that the implementation is really a transliteration of the algorithm into the as a code. So you have a XOR of 3 variables, and here we have the SBox call of this variable. We use the key and the last variable. After that, we have the addition with round constants, and we have the permutation. So if you want to compute these things, in fact, we have several ciphers that are already implemented into Tagada. So to do this, you just need to call the execution of the ciphers and provide the parameters that are indicated by the authors. In the case of AES, namely Rindal, you can change the size of the plain text and the size of the key. And you can also define the number of rounds. So if you want to test that the cipher is correctly implemented, you can provide, you do not provide the number of rounds, and you have the full version of AES. And after that, you will be able to test if the implementation is correct. On the second part, you have the same example for 3 rounds of warp. So you just say the number of rounds you want, and it generates the data. So in fact, I show you a quite simple example of a DAG representation. In real ciphers, the models are much more complicated to debug. As you can see here, you have only 3 rounds of AES. So to be able to have the full AES version, you need to have at least 10 rounds. So in fact, you have colors that help you to debug the information. The red one at the end are the output of the ciphers. The purple one here are the plain text, and the yellow one here are the key informations. And you can see that all the yellow states that are colorized in the cipher are the states that belong to the key schedule. Okay, so with this representation, the first thing that we are able to do is to check if the representation of the DAG is correct. So here we just show that we have the AES test vector, and we indicate that we are able to evaluate one plain text and white key, and to check if the output correspond to the expected cipher text. So now I will present how Tagada works in order to compute the differential characteristics. So in differential attacks, we want to evaluate the probability to observe a given output difference when we inject an input difference delta m in the plain text, and eventually an input difference delta key in the key if the attack is a related key attack. So the problem is that we only have a cipher representation, and that we want here is no more to be able to evaluate the value C when we have the input that are fixed, but we want to be able to compute the probability to observe the difference delta C when we know that the difference delta M are fixed to a given value, and delta K that is also fixed. So to do this, we need to compute a few things. So firstly, we define the probability to observe the full differential characteristic as the probability to observe each operation independently, and to compute the full probability, we multiply each component probability to obtain the full evaluation. So in order to be able to compute this probability, we need to be able to evaluate each operation probability. For the linear operators, it's quite simple. The probability in the differential is 1 if the values of the input and the output are correct. And if they are correct, if they are not correct, the probability is 0. And in the case of S boxes, which are nonlinear operators, we must use the DDT tables in order to be able to evaluate the probability. So in this step, we use some techniques. Firstly, when we have a XOR with a constant, we remove the constant during this step, as the constants are cancelled in differential attacks. And we compute the DDT of the different S boxes in order to be able to evaluate the probability. And we transform the original graph into a new graph, which is a differential graph, which do not anymore represent the cipher specification, but have a specific meaning in order to be able to compute differential characteristics. So if I take the previous graph, that will be the model that we internally compute into the library. So we see, for example, if we use nibble variables, we have the 4 states that are defined as variables. After that, we have computed the probability of the S-box transition. For example, we have I've given some random values for the S-box transitions. We have probability 1, probability 2 to the -2, and 2 to the -3. You can see that we do not represent null probabilities, as they are not interesting in a solution, and it will generate much more solution if we add the null case. After that, we put some constraints. So we indicate that the output difference of y should be equal to the input difference of m and the XOR of the input difference of k. We add the constraints that the variable delta y and delta c must be linked with a given probability. And the given probability is set by the DDT that we already compute. So in fact, here we have a list of possible values which link which input difference is linked to one input difference and with its respective probability. And at the end, we have the objective variables which which to be maximized, which is the probability of the differential. Here we have only one S-box, but if we have several S-boxes, we multiply the probability of the different S-boxes. So when we have the first data representation, so the specification graph, in order to differentiate the specification graph into a differential graph, we just need to call this command line, and this will automatically convert the first graph into the second one. So as indicated in the title, Tagada is a tool that is truncated based solver. So we need to compute one abstraction in order to perform quicker computation, faster computation. And in this step, we want to compute truncated differential characteristics. So in the case of a differential characteristic, we know what are the values in the differential But here we do not want the specific values. We just only want to see if there is an input difference, an active difference in the plain text or in the key, and how this difference pattern is propagated to the ciphertext. So in fact, for the variable, it's quite simple. Each word is abstracted by one Boolean variable, and we need to compute the abstraction of the operators in order to be able to indicate where the difference is propagated. So now we do not want to compute what is the probability to observe delta C, knowing delta M and delta key, but we want to observe what is the probability to have one output pattern, knowing that we have an input pattern that is active in the plain text and in the key. So as for the differential, we indicate that the probability of the pattern is the multiplication of the probability of the components. And also here, we need to perform several computations. The first computation is to transform each variable into a Boolean variable, which is quite simple. And the second part is to abstract the operations. So the way we do this in Tagada is that we exhaustively compute the possible inputs of each operators, and it will generate all the possible truncated solution for these operators. With this computation, we are able to find back the MDS property of the mixed column of AES and the quasi-MDS property of the mixed column of Midori. For the DDT, now we just know that the best solution possible is at most the best activation probability of the DDT. So in the case of the DDT, we just keep the highest transition probability. Okay. It's just a mistake. So for the big delta M and delta key and all the variable, it's just between 0 and 1. For the probability, as I said, I just keep the best probability. And for the constraints, what we do is that we translate the different operation into truth tables that indicate which input patterns leads to which output patterns. And for the DDT tables, we just indicate that an input is active with at least the activation cost of the probability. And at the end, we set the objective to the probability of the S boxes, and we want to maximize the probability. So in order to compute the abstraction of the differential graph, we can use this command. So this command will allow to add some improvements, which is redundant XOR generations, differential variables, and transitivity, which is a work that was done by David Gero and co-authors. So in the case of MDS or pseudo-MDS properties, the abstraction of the operators which will lose a lot of information, and we need to add redundant equation into the abstract model in order to have enough strong model in order to be able to compute the correct truncated characteristic. So if we want only to search the truncated differential characteristic, when we have computed the differential characteristic graph, you just need to call the this command line, and it will generate the output with the objective. The objective have a specific representation, which is translated into the right of the picture. Now, if we want to compute the differential characteristic, we need to have both the truncated graph and the differential graph, and we can compute the solution as is. So our results, in fact, when we start to write Tagada, our objective is to provide an efficient tool. So in the first step, we saw that we have a solution that is close to the best possible solution at the time with a fully automatic solution. And in the second time, we check the full analysis of the differential characteristic, and we were able to find back the result of different papers. So the library has some drawbacks, and we need to write on a few things. So if we do the history of the library, initially it was it was written in Python, Ruby, and Rust. We use Rust because we need some components that need to be really quick. And in the second version of Tagada, we also add Kotlin and Java, as we need to have constraint programming solvers, and they are mostly written in Java if we want to be able to create a new constraint directly into the engine. And now we are currently in a refactor of the code base in order to remove the Rust part and in order to simplify all the code base. So the working directories are, if we want to improve the quality and the speed of the resolution, we need to create dedicated constraints. So we know that we have a really poor abstraction process for the XOR. In the second step, so maybe we need to create a much more efficient XOR constraint. The problem is that how do we handle large S boxes? If we have large S boxes, the transition probabilities will be hard to evaluate. We also may need to include information specific to cryptographic problems. So in our current representation, we do not have the notion of a round and a thing like this. And it's really important to add them because we are able, if we have more information, we are able to detect false positive solutions and to break cipher symmetries in order to to improve the resolution speed. We need also to improve abstraction of truncated attacks to have tight truncated solutions, and to be able to handle bit-oriented ciphers. And at the end, we expect to implement new attacks with new key recovery solutions. Thank you for your attention. I can take any question. In fact, the code base will be written in Java because for the first step, the solver we previously used was PCAT, and we communicate with it through Minisync. But our tools provide a Java interface, which allows us to directly communicate to the solver with only a Java call. And it will be the main advantage of this translation is that we will be able to perform pre-processing before giving the model to our tools. And it will be much easier to do this in Java than doing this in Minisync or things like this. And yes, for the second part, we expect to use Choco. Yeah. Yeah, but in fact, we use external solvers, but the solvers can be directly integrated into the library. That was not possible in the version 2, because if we have Minisync or PCAT, we need to add to install PCAT or Gurobi as a standalone application and call them. But with Choco and OR tools, they are already embedded into the library, and you just need to install Tagada.